In this paper, we introduce a general, dictionary-based learning method to evaluate the fidelity of any traffic trajectory data. For illustration, we first show the evaluation result of a simulation data, with comparison to the real-world traffic flow. In computer graphics, researchers have developed many methods to simulate traffic as realistic as possible. However, a fundamental question has been largely underexplored. How can we evaluate the realism of a synthesized traffic flow? There are several challenges. For instance, the complex traffic dynamics might be hardly captured, and the real traffic data is usually unavailable. Here, we present a dictionary-based metric by building a dictionary from real-world traffic. The corresponding learning error is defined as the benchmark of dictionary representation. To evaluate the fidelity of virtual traffic, we then reconstruct the simulation data, using the built dictionary. Finally, the fidelity can be evaluated by error comparison. We applied our metric to 3 different traffic simulators. Each method was tested with 3 variations of parameters, with label 1, 2, and 3. For all the generated virtual traffic, we performed the perceptual study for comparison. The first tested scenario is low-density traffic flow. The simulation with lower dictionary-based score shows flexible acceleration behaviors. Remember that the lower dictionary-based score represents the higher fidelity. For the perceptual study, higher value means better fidelity. The second scenario is traffic flow and high density. The result on the left-hand side shows better fidelity. Because traffic congestion with flexible braking and lane-changing vehicle behaviors can be clearly observed. We highlight them with yellow circles. The third scenario shows the traffic flow in a detailed junction of a highway network. The virtual traffic on the left-hand side with stop-and-go behaviors is more realistic than the right-hand side. Also, all the vehicles on the right side behave similarly in a uniform way, that gives them lower fidelity. The last scenario is a traffic light-controlled flow. On the right-hand side, several vehicles exhibit abnormal slow behaviors at the zebra crossing, which makes it get higher dictionary-based score. Whereas the result on the left side is more realistic. Vehicles gradually stop when the traffic turns red. Here we can see that our metrics are strongly correlated with the perceptual evaluation outcomes. We also compare our method with the entropy-based metric. This is the simulated traffic flow, that hardly matches the real-world data. In this case, the dictionary-based metric and entropy metric both get very high scores. In this video, the virtual traffic can match to the real-world data better, in terms of the flow velocity. We chose better simulation parameters, to decrease the scores of the 2 metrics. The traffic simulation with the lowest metric scores, presents the highest similarity to the real-world traffic data. The video shows that, individual vehicles on the right side, can mostly match to their real-world counterpart on the left side. Through above comparisons, it can be seen that our method is competitive to the entropy-based metric. The main advantage of the proposed dictionary-based metric is that, it doesn't need any real-world data as reference. Moreover, this method has broader applications, because it can be directly applied to any traffic simulators.